So today's lecture is going to be on chapter 4, which is about torsion. So we will talk about torsion in shafts, and because of the torsion, we're going to see shear stresses and we're going to see shear strain, and we will talk about how to calculate those shear stresses and shear strain, what is torque, what is torsion, and because of those torsion and torque, you're going to see twisting of those circular cylinders. So we're going to see like when you have twisting, then what is the angle of twist. So this chapter is going to be about circular cylinders. So like rectangular cylinders and other shapes are outside the scope of this chapter. So we'll only talk about a circular cylinder in this chapter. So this chapter is about circular cylinders, and we'll see when you apply torque on those circular cylinders, then what happens? Either you get like normal stresses or shear stresses, and also if you have torque, uh, what are those stresses and the twisting and torsion. So in chapter 3, what we have discussed. In chapter 3, we know when you have a member and when you apply a force on that member, then you can imagine how the bending will be, like how it will deform. So it will deform something like that. So you will have a elongation. So what we were talking in chapter 3 was about normal forces and normal stresses. So for example, if you have, this is called longitudinal axis, right? So when a force is being applied parallel to the longitudinal axis, this force is called axial force. We can also see that this force is making a 90-degree angle with the cross section. So this force is also a normal force. And normal forces produces normal stresses and normal strains. And if you want to imagine how it would change the shape, it will cause elongations mostly. That was chapter 3. Now let's see what happens when I change the force. So instead of force, I will apply, let's just say, bending moment this time. So this is a simply supported beam. If you apply a bending moment, so you can imagine what will happen, like how this member will change shape. So I can draw a change in shape. So this is how the member will kind of change shape under the influence of this bending moment. So this is a moment. So when you apply a moment, this is how the member will change shape, will deform. And I can give you another example. So if you have a member and if you apply a moment on other direction, so this moment will actually change shape of a member in terms of twisting. So what this moment will do is that it's gonna try to twist the circular cylinder. So if a moment is causing twisting, then this type of moment is called torque. So torque is nothing, it's just a moment, but it's acting in a different direction, which is not causing bending, but it is causing twisting. So if you have a traditional normal moment, it's going to cause change in shape, and this change in shape is called bending, which we will study in coming lectures. But this chapter is about torque, and this chapter is about torsion. So torque is also a moment, which is force into distance, moment arm. But this torque is that kind of moment which is acting in some direction which is causing twisting. So when a moment is causing twisting, then this type of moment is called torque. And when a moment is causing bending, then this type of moment is a normal moment, which is also called bending moment. So that's torque, which is causing twisting and torsion. Twisting is also called torsion. So torsion is a technical name of like twisting, which is caused by the torque. So this is what we will talk about in this chapter. So what's torque? By definition, torque is a moment, but it is a special kind of moment which will cause twisting. So that's the definition of a torque. So torque is basically an external load. This torque is an example of external load. So we have like external loads, you have then reaction loads, and then you have internal loads. So it's an external load, and as a reaction you will have a reaction load, and you can also calculate the internal loads from equilibrium equations. So in this figure you can see that these are the applied loads. This is the torque. This is also, so this is a torque. And what this torque is doing, you can imagine if you apply a torque, then it's going to try to change the shape in a twisting way. So it's going to try to twist this circular cylinder. So what is torsion? So torsion is defined as twisting of an object caused by moment acting about its longitudinal axis. So basically, applied load is called torque, and the actual twisting, so it's going to result in twisting. So twisting is also called torsion. So what I want to say is that torque produces torsion. So torque is a moment, and it is a special kind of moment which is causing twisting or torsion. So this is what we are going to discuss in this chapter 4. So chapter 4 is about the torque applied forces. Chapter 3 was about normal forces. So in chapter 3, when you have force, you saw what is how to calculate stress, how to calculate strain, how to calculate elongation. Now the applied load will be torque. It will not be a force. So when you apply a torque, it will cause torsion. So we'll try to calculate this torsion, change of shape, in terms of the thing which we call angle of twist. And because of these torque and torsion, we will also see that either it is producing like normal stresses or shear stresses, what kind of stresses it is like producing, and we'll also try to calculate those stresses. So we can also further elaborate the concept of torque. So for example, this is a circular cylinder. So if you want to imagine how twisting happens, so what you can do is that you can like arbitrarily draw lines. So if you draw a straight line on a circular cylinder, and if you also draw cross-sectional lines, so when you will apply a torque, you can see those lines changing. So this is how like torsion, you can imagine torsion by looking at those lines, and this is what's going to happen on a circular cylinder when you apply a torque. So this is twisting. This thing is called twisting, or you can say torsion, because of the applied torque. So you can see what is happening. So the circular cross-sectional lines, you don't see any like twisting or bending in these lines, but you can see the straight lines have changed their distances. So this is what is going on when a circular cylinder is being applied torque. So this is torsion and twisting. So if you just take one line out of it, of a circular cylinder, so this is a one line. When you applied torque, so this one line, there are many lines, but if you take out just one line, this one line will linearly increase along the length of the member. So I'm gonna take a cross-sectional area here out. So this was the original line, and when you apply torque, this line kind of moved to this position, right? So this was originally, and when you apply torque, it goes to A prime. So this angle is basically a representation of actual twisting or torsion happening. And this angle is called angle of twist. So if you can calculate the angle of twist, you can try to understand like how much twisting is happening because of this applied torque. And also this angle is strain, but we will see that in a while. And this angle is called angle of twist. And you can also see one more thing. For example, if you take any part out, so I'm gonna just take this one part out. So you can see it's a kind of a perfect square. But after twisting, if you take the same part of the section out, you're gonna see something like that. So if you apply torque, the individual elements or the surface of the section are gonna deform, are gonna change shape. So originally, this was originally like this, which I've taken out from before when we apply torque, and after when we apply torque, I've taken out this. So you can see it's like it has changed shape. So the question is like either in normal stresses you have a change in shape, or in shear stresses you have change in shape. So in chapter 2 we saw that when you have a change in shape, that change in shape is because of shear stresses. So from here we can know that the torque and torsion is producing shear stresses because it's changing the shape. So that's why torque produces shear stresses and shear stresses produces shear strain. So in chapter 3 you had normal stresses and strain. This is chapter 4. We are talking about torque, and torque produces angle of twist, and also we can see that you have change in shape. You're not having elongations in the part of the section. You are having change in shapes. So whenever you have a change in shape, that change in shape is because of the shear stresses. So torque will produce shear stresses and shear strains. You can also further see if this was the line before. When you applied torque, that line moved here. This is called angle of twist. And when you haven't applied torque, it was kind of like square. But if you apply a torque, then the parts of the circular cylinders have changed shape. And change of shape means that you have shear stresses and shear strains in it. And this is the formula for angle of twist. So if you know these values, you can calculate the angle of twist. And angle of twist is actually a representation of the amount of torque being applied on a circular cylinder. And that's the formula. This is angle of twist. And if you see a circular cylinder, after torque is being applied, this angle is called angle of twist. So the more torque is being applied, the more would be the angle of twist, depending upon other parameters as well. So that's the amount of torque which will be applied on a circular cylinder. This is length of bar which is this distance. This is the length of a bar. This is polar moment of inertia. So this is a moment of inertia, but this is a polar moment of inertia. So moment of inertia is a geometric property which you have like studied in mechanics, in statics. So polar moment of inertia is also a type of moment of inertia, but moment of inertia actually resists bending. So polar moment of inertia resists torsion. So that's the only difference. And this G is shear modulus of elasticity. And you can calculate G, shear modulus of elasticity, from Young's modulus of elasticity as well. So if you know standard material properties, which is modulus of elasticity and Poisson ratio, so for a circular cylinders, you can calculate shear modulus of elasticity from this equation as well. So this is like modulus of elasticity, or elastic modulus of elasticity, or Young's modulus of elasticity. This is Poisson ratio, which we have calculated in chapter 3. So if you know these values, you can also calculate shear modulus of elasticity. So that's how you can calculate the angle of twist. And this J is polar moment of inertia. And this polar moment of inertia, this equation is for circular cylinders. If you have a solid bar, you can calculate the moment of inertia, polar moment of inertia, by using this equation. So basically, if you know the radius of a solid bar, then you can calculate the polar moment of inertia by using this equation, where this is radius of a circle. And what is a polar moment of inertia? Polar moment of inertia is cross sections resistant to torsion. So you know what moment of inertia is. Moment of inertia is a geometric property. So moment of inertia you can calculate just by looking at the shape of an object. And what moment of inertia does is that it provides you resistance towards bending. So polar moment of inertia is a moment of inertia, but it's a polar moment of inertia which is gonna help resisting torsion. So it's also a geometric property. So you can calculate by just looking at the shape of an object. So if it's a solid bar, you can calculate polar moment of inertia by using this equation, which is pi by 2r4. So this polar moment of inertia is a geometric property. And all the geometric properties you have studied in statics. So in statics, what you guys were studying were basically geometric properties. And this G is actually material property. So different materials have different G's. And E is also material property. Poisson ratio is also material property. So material properties, which we are like some studying in this subject. So material properties depends on a material, and geometric properties depends on the shape of the object. Okay, so we know that torsion actually change shapes, right? So if you apply a torque, you're gonna see change in shape. So we know that torque is producing shear stresses and shear strains. And these are the formulas for calculating shear stress and shear strains. So this is shear strain, which is this value. So we had a line straight. When we applied torque, the line moved to a different location, and the angle, this angle is called shear strain. And this is called angle of twist, which is the actual twisting. So I'm gonna take this thing out and we're gonna draw it here. And I'm gonna take this thing out and we're gonna draw it here, which is change in shape. So it's kind of like changed in shape. This line has moved upward. Before it was here, so now it has kind of moved a little up. So we know it's moved up because of some force, which force is called shear force. And if you use equilibrium equation, you will know you must have another force which is equal in direction, equal in magnitude, opposite in direction. And this is gonna cause anti-clockwise movement. So you know, to counter that moment, you must have another two forces up and down as well. And these forces are called shear forces. So this is shear strain. This we already know. This is angle of twist. This is length of a bar. And this is the radius of a bar. And all these equations are for circular cylinders. These equations are for bars. Because if you have another shape, then it's gonna have some other deformation types. So these equations will not be applicable there. And in chapter 4, we'll only talk about the bars. So these equations are valid for our purposes. This is shear stress. This is torque. This is, we know, is radius. And this is polar moment of inertia. So using these equations, we can calculate the angular twist, we can calculate shear stresses, and we can also calculate shear strains. And these equations are basically coming from these figures. I can show you one of the example, like how we can calculate these equations. So for example, if I take this triangle out of it, so this is B distance, this is B point, this is A prime. So this is A prime. This is kind of like 90-degree. So if you do tan of this angle, so we know tan is perpendicular over base, right? Perpendicular in our case is A by A, and base in our case is this distance, which is L. So this is AA, this was A, this was AA, this is the angle theta, this is distance R. So we know this distance is r theta. So we can replace AA by r theta, and we also know tan theta is approximately equal to theta for a very small, if the angle is really, really small, tan theta is approximately equal to theta. So by using this, we can calculate, we can just replace this with this. Theta would be equal to r theta by L, which is this equation. Similarly, you can also calculate for stresses. Stresses would be like you have to integrate individual stresses on the bar, and then you can calculate for the shear stresses. But for our purposes, if you know these equations, then we can calculate everything we need to calculate. So we have these equations, angle of twist. Uh, we can calculate shear modulus of elasticity from Young's modulus of elasticity and the Poisson ratio. This is the formula for polar moment of inertia for circular cylinders. And if you want to calculate shear stresses and shear strains, so these are the equations to calculate shear stresses and shear strains. So now we can do first example, depending upon how much time we have. So this example, this is the first example in the workbook. This example says consider two right circular cylinders, each with a fixed gear to a rigid wall. So this is a rigid wall. And this is gear A, this is gear B, and the first shaft. This is shaft 1, this is shaft 2, and the first shaft is made up of brass. So the first shaft is made up of brass. These are the material properties for the brass. So material property, the Young's modulus of elasticity is 100 gigapascals, and the Poisson ratio for the brass is 0.34. So I put 1 because shaft 1 is made up of brass. Shaft 2 is made up of aluminum. So the material properties for aluminum in terms of modulus of elasticity and Poisson ratio is 70 gigapascals and 0.33 is the Young's modulus of elasticity. So it says L1 is 10 centimeters and D1, the diameter of the shaft 1, is 1 centimeter. Second shaft is made up of aluminum. The length of the second shaft is 8 centimeter and the diameter of the shaft is 1.5 centimeter. Gear A has a diameter 40, so this gear has diameter 40 centimeter and is loaded with a force is 800 Newton. Gear B has a diameter of 30 centimeter and is loaded with a force of 1200 Newton. So it's a little more complicated than what we were talking about in chapter 3. But basically what you have to do is you have to calculate torque in this case. If you can calculate torque, then the rest would be a bit easy because we know the equation for angle of twist, we know the equation of stresses and strains for a circular bar. So the trickiest part would be to calculate torque. So if you can calculate torque, then you can calculate the shear stresses, shear strains, angle of twist, and everything. So let's talk about part A. Part A is we have to calculate, so we have to figure out what torque is. So it says calculate Tx and Tz, but let's calculate all the reaction forces and then we're going to figure out which one is torque and which one is moment. So the first part is to calculate the reactions. So let's try to calculate all the reactions. So for that we need to draw a free body diagram. So if I'm gonna draw a free body diagram, that's how it will look like. So it's a fixed support because it's a rigid wall. It's fixed to a rigid wall. So this is a fixed support, and I can try to draw this cylinder. And I'm gonna draw this cylinder as well, just for you guys to make it like easy to understand. And we know there is a force which is being applied at the end of a gear A, and that force is FA, which is equal to 800 Newton. And then there is another force which is being applied on gear B, and that force is 1200 Newton. So let's decide the coordinate system. So the coordinate systems are already given. So this is x-axis, positive x-axis. Upward direction is positive y-axis, and out of the plane is positive z-axis. So this is a kind of a three-dimensional problem. So now we have 6 equilibrium equations, and you have 3 reaction forces, and you have 3 moments along 3 different directions. So I'm going to try to draw these reaction forces. So this is one force which is acting along x-axis, the reaction load. This is another reaction load, and let's draw this way to make it more clear. So you have one reaction, and there's another reaction here, but I'm going to draw it here to make it more clear. And then you have a reaction along z-axis. So let's call this one Rx, reaction along x-axis. Let's call this Ry, reaction along y-axis, and let's call this Rz, which is a reaction along the z-axis. And you can calculate these reactions by using equilibrium equation. Summation of forces along x-axis is equal to 0, summation of forces along y-axis is equal to 0, and summation of forces along z-axis is equal to 0. But this is a fixed support. So in addition to all these 3 reactions, you will also have 3 moments. So let's try to draw these 3 moments as well. So you have a moment along x-axis. This is moment along x-axis. You have a moment along y-axis. This is moment along y-axis. And also you have a moment along z-axis. So these are the total reaction loads you will see because of the applied loads. So you have external loads which are shown in red, and you have reaction loads which are shown in blue. So we can try to solve all those reactions, but you can try to think that which of those moments is going to cause bending and which of those moments is going to cause torsion. So there is one moment which is actually going to cause twisting of these bars and shaft. So you have to figure out which is that moment. So there's one moment which is causing twisting, and the other 2 moments are causing bending. So let's try to find the reactions. So let's do summation of f of x is equal to 0. So if you do summation of f of x is equal to 0, I can see only one force which is acting along x-axis, and there's no other force which is acting along x-axis, so r of x is equal to 0. If you do summation of f of y is equal to 0, so you have r of y, and then you have negative f of a, and then you have negative f of b is equal to 0. So this f of a is 800. This is 1200. So if you calculate, you'll get the value of Ry as negative 400 Newton. So if you do summation of forces along z-axis is equal to 0, I don't see any force, so R of z is equal to 0. Yes.
Why is that B negative?
F of, yeah, okay, good, good, good. So f of b should be positive, right? Yeah, but you'll get negative 400. So yeah, good, thank you. So let's see, what is this distance? This is center, right? If this is the center, what is this distance? This distance is actually 40 by 2, which is 20 centimeter. And this distance is actually 30 by 2, which is 15 centimeter. These distances are these distances from center to here, which is actually half of the diameter. So what I want you guys to do is do summation of moment along x is equal to 0, summation of moment along y is equal to 0, summation of moment at z is equal to 0, and give me the values for moment along x-axis, moment along y-axis, and moment along z-axis. So you guys can try to do and let me know what values you are getting for the moments along x, y, and z. So if you do summation of moment along x is equal to 0, how many forces are acting along x-axis? Like how many moments? So this is one moment, and you also have to decide the direction of the moment. So I mean, I have drawn it this way. So if you try to see the direction, so this moment x is acting along this direction. So the curl of the fingers is towards where the moment is acting. So the thumb will point the direction of the moment. So in this case, the direction of the moment is opposite to what we have decided as a positive x-axis, right? So the positive x-axis given is in this direction, but I've drawn the force in such a way, moment in such a way that the direction is opposite to the direction. So I'm going to put negative m of x for this moment because this is opposite to that, yes. So this is the moment, right? So that's how the moment is, right? Is it you're seeing like this? This m of x. This m of x is rotating like this, right? Huh? Does it make sense? Like this? You guys are swinging like this? I don't know. I mean, some guys can see. Okay. So if you think the moment is like this, then you can put positive direction in that case. But there's a nicer way to do, because instead of doing this, we can put double arrow, then it's gonna make it more clear. But if you think the moment is this, then for sure it should be positive. But I feel like the moment is like this, so I'm gonna put negative. Yeah, to me it feels like it's like this. So I'm gonna put negative. Okay, so now you guys can calculate and let me know the values. Let me know what the value of the moment. Does it make sense? Is it easy or is it difficult to calculate? You can think about it, because this is important. Once you need to know the value of torque. So if you can calculate the moments, then you can figure out what's the value of torsion, And if you know torsion, then you can calculate angle of twist and shear stresses and shear strain. So this is very important. So you guys can try to see what's the value of torque.